Alright guys, today we're doing Level 3 Physics 2017, Demonstrate Understanding of Wave Systems. Question 1. So question 1 starts off with some pretty useless information. The first two sentences are pretty much crap. Just ignore that. We'll start here. It says, a clarinet can be modelled as a pipe that is open at one end and closed at the other. The length of the clarinet is 0.613 meters. The speed of sound is 341 meters per second. On the diagram below, draw the first harmonic standing wave and label the nodes and antinodes. Alright, so this is pretty standard. If you've forgotten what a fundamental standing wave looks like for an open-closed pipe, which is evident with the open and closed end, as it tells you, just looks like this. This is a very wobbly version of it. There. It's supposed to be about a quarter wavelength. So if you can imagine, that's about a quarter of a wave, a full wave being something like that. And it says also label the nodes and antinodes. So we'll just go an N for a node, which is minimum, and A for antinode, which is maximum. Alright, question B asks, the clarinet produces the fundamental frequency and several harmonics. Explain why the clarinet does not produce any even harmonics. Well, we can start off by stating what type of pipe this clarinet is. As we talked about before, it's open at one end and closed at the other, so it's an open-closed pipe. And we know that because there's a node at the closed end and an antinode at the open end. So there we go, just starting off statement. Now, as we stated before, in an open-closed pipe, we can only fit quarter wavelengths in. In fact, we can only fit odd quarter wavelengths in. So that's like quarter lambda, 3/4 lambda, 5/4 lambda, etc. And so by stating that, we can say that in open-closed pipes, only odd quarter wavelengths can fit into the tube, or the length. And I think that's why they actually give you the length, because you don't actually need to use this for any of the other questions. So if you're ever stuck, I suppose you could just figure it out by yourself. But it's actually easier just to remember that in open-closed pipes, they only progress in odd quarter wavelengths. And so your last statement is just going to be a general one. It's just going to say, as a result, it can only produce odd harmonics. Alright, question 1C. When the train was approaching Ballot at a speed of 5 meters per second, he heard a frequency of 139 Hz from the clarinet. Show that the frequency of the sound heard by the clarinet player would have been 137 Hz. So from this, we can probably gather that it's a Doppler question, which means we're going to need the formula of... And so just like a recap, F1 is the frequency perceived, F is the true frequency, VW, both of those, is the speed that the wave travels in the medium, and for this we know that VW equals, what was it back here, 341, because it told you at the start. And Vs is the speed of the source, which is 5. So we've got some info. And it says he heard a frequency of 139. So knowing that he heard it, we know that F1 is also going to be, is going to be 139. Now the tricky part with these types of questions, knowing whether to use VW plus Vs or VW minus Vs. So how I like to think about it is, if a police officer is coming towards me, generally I see that as a negative sign. So whenever something's coming towards, I just remember, okay, that's negative, so it's minus. But if a police officer is walking away from me, I'm like, hallelujah, thank God they're not coming after me, and that's a positive. So in this case, the train was approaching, police officer approaching, bad, so it's negative. So we're going to use minus, and I'll write in the info we know. So 139 equals F, and then it's going to be 137 when we figure it out, but I'll just leave it as F. And then it's going to be 3, 4, 1 over 3, 4, 1 minus 5. And then you just got to isolate F by itself, and you should get your F as what it states, 137 hertz to 3 significant figures. Alright guys, now we're on question 1D, and this one is a doozy. So we're going to try to do it step by step. It says a second clarinet player was standing beside Ballot as the train approached. She produced the same frequency as the clarinet player on the train, causing Ballot to hear beats. Explain why the sound wave reaching Ballot from the clarinet on the train did not have a frequency of 137 Hz, and explain why Ballot heard beats and calculate the beat frequency. So obviously this is a packed question. I mean, it's almost 3 questions in one. And if I'm completely honest, NCEA were probably running out of space, out of paper, like on the actual exam, so they were just like, alright, let's just chuck them all in one. Anyways, let's do it step by step. The first one, explain why the sound wave reaching Ballot from the clarinet on the train did not have a frequency of 137 Hz. Well, I think the easiest way to start this sort of answer off is to explain Doppler. So as the train approaches Ballot, there is relative motion between the clarinet and him, the observer. So there is a change in perceived frequency, and that's basically Doppler's effect. So next up, you want to state why he's hearing a higher frequency. And if we just go back to this question, it tells you that he heard 139 instead of 137. So we know that the clarinet is moving towards him, so we'll just state that. And then we know that V equals F lambda, the equation, so we can relate to why he's hearing a higher frequency with that equation. So the clarinet on the train is moving towards waves, and so that basically means the wavelength is decreasing. If we relate that to V equals F lambda, assuming that the speed of sound in the train is constant, this means that V is constant, and so since we said before wavelength is decreasing, frequency must be increasing as they are inversely proportional, and that is why he hears a higher frequency than expected. Next up, we're talking about beats. Explain why Ballot heard beats. So just want to start off with the definition of beats. Beats occur when 2 slightly different frequencies, so obviously slightly different wavelengths, are heard at the same time. The interference between the waves creates a perceived change in volume and or pitch, I suppose. So to explain the louds and the softs of beats, we can probably use an explanation. And that is just talking about wave interference, really. So when the waves interfere in phase, blah, 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 constructive, max amplitude, antinode, so it sounds louder. Same thing out of phase, when they arrive out of phase, destructive interference, minimum amplitude, so it sounds quieter. Pretty straightforward stuff. And finally, we get to the last part of this mega question. All you got to do is figure out the beat frequency, and it's pretty easy with this equation. It's not given to you, but it's not hard to remember either. So FB equals F1 minus F2. And F1 is just whatever the bigger one is. So F1 in our case is 139 minus F2, which is 137. And you don't even need a calculator for this. It's just 2 Hz. And that's the answer.